Okay, so active constituents. The model right now, there are 36 potential water quality constituents in this code. You do not have to, you do not have to run all 36. Okay, you can arbitrarily turn constituents on and off. Be careful, all right, so you can arbitrarily turn constituents on and off. Now, in the kinetics, many of these constituents are linked. And at this point, there's nothing in there that'll prevent you from doing things that are inconsistent. I'll make something up. If you said, I don't want to run temperature, temperature is necessary to compute algal growth rates. So you're never going to get an error that's going to say, oh, you can't do this because you want to run algae. It's just going to pull temperature from Lord knows where, okay? So you want to be a little bit careful about what you turn on and off. On the other hand, for example, there are, well, we're going to look at some variables in a few moments, but there are, let's say, sediment transport variables where if you decide not to run sediment transport, you can turn those off with no consequences, okay? There are also variables in here that are obsolete. Well, we'll look in a few minutes, but in the control file, there are 36, we're over on this side, over here. There are 36 ons and offs. It's that simple. You turn them on, you turn them off, and once again, A, that's formatted, B, uppercase and lowercase matters. You notice that's all uppercase, don't use on lowercase, it's not the same, Okay, so be it. And let's see what the next slide is. Okay, so I just mentioned this. This is from the code, from the sizes module. If you think about it, all the arrays in the model require dimensions. And there are some fancy things you can do now with this, but for now, you set the dimension of the arrays in this module sizes. And so for example, NCP is the number of constituent parameters, and you see it's set to 36. Tom, he made this code initially to be as flexible as possible. So if you want to add a few variables, you can make that 42, if you wanted to. What I do is, it turns out that since not all 36 of those variables are utilized at any time, I might, just for example, silica is still occupying 2 places. We don't simulate silica anymore. So suppose you said to yourself, I want to add pathogens to the code. I'd probably use whatever silica is and substitute pathogens. If you chose, you could make that number 37 and add pathogens, to the bottom of the list. But that's 2 ways of doing it. In any event, don't mess with that one. But here, these are the sizes of arrays. It's the number of boxes, the number of flow faces, the number of, I guess that's horizontal flow faces, the number of surface flow faces, and the number of surface boxes. This is for the bay. Now, these set array sizes, they can be bigger. They don't have to represent exactly the number of faces or the number of cells. Okay, the actual number of faces and the actual number of cells are specified in the control file. What we're doing here is setting arrays. By coincidence, these are actually exact numbers. The Bay model has 56,920 cells. It has 11,064 surface cells. So we set these exactly. Like I said, they don't have to be exact, but they do have to be big enough to allow. And if you look at the control file again, way up here at the top of the control file, these are the actual parameters for the model. And actually, you see here, this illustrates, these parameters are set for the 30 box model. Number of boxes is 30, 10 surface boxes, a total of 51 flow faces, 31 horizontal, 11 in the surface layer, 3 layers. You know, these are, okay, but you saw in that parameter statement, that was relic from the actual Bay model. So even though we allowed for 56,000 plus boxes, we're only using 30 of them, and that's okay, you know. Let's go ahead on. Here's the magic key. And I think, Richard, you handed this out. Did you hand?
Yes, I put the one sheet that have their list. If someone do not have it, I can have more here.
Yeah, later on, what's going to happen is when we actually run that 30 box model, you're going to be prompted for what number variable you want to plot.
Oh, yeah.
So you'll want this correspondence, because if you want to plot oxygen, you don't type in oxygen, you type in 27. So here, I mean, these are the 36. Now, like I said, there were relics. We no longer simulate zooplankton. And I don't mean, it's not even in the code anymore. It's just gone. Let's see, anything else? So, here, in any event, here's the key. This is what we simulate. We're going to talk, I guess, tomorrow. We're going to go over the kinetics in detail, and we'll look at each one of the variables. As I said, for example, you can see that these are from a sediment transport model. You can turn those, you know, if you're not simulating sediment transport, you turn them off. Other ones, you know, probably temperature is something you don't want to turn off because you're liable to get in trouble. You could easily, and we do on occasion, for example, run a temperature and salinity model with nothing else. You know, if you're just trying to calibrate transport, or you want to check your ICM model against the original hydrodynamic model, something like that, you might just turn on temperature and salinity and run a very simple model. Go ahead.
Why would you run temperature? I mean, just the reason I'm asking, just thinking of what we do. We do include salinity in the R models. It's just a way of checking against the hydrodynamic model, making sure we're not losing some information in the processing. But why temperature? Because it has forcing functions. Do you specify those forcing functions for the temperature then?
You would have to, yeah.
You would. But you could you skip temperature and then, but that's not read in from your hydrodynamic model, I see.
No.
Okay, all right.
You could just run salinity
Right.
if you chose to. I just picked temperature and salinity for whatever reason.
Right.
Yeah, if you run temperature, then you need to specify the atmospheric forcing functions that...
Well, why wouldn't you just pick that up from the hydrodynamic model? Or why wouldn't you?
initially, because we wanted to keep the file small.
Oh, okay.
And go back 30 years. And we decided that it'd be easier to compute it than it would...
Store it, okay.
Than it would be to store it, yeah. So, okay, let's go down. Where do we go? Okay, these are the state variables that are actually enabled in the Chesapeake Bay model. So, and you, let's see, go 1, 2, 3, you know, go across temperature and salinity, fixed solids. The model has two representations of solids. The fixed solids are inorganic suspended solids, and they've been in the model from the beginning. We later, you know, added sediment transport. I don't know if I've got the sediment transport variables in here. There's also, if you run the sediment transport option, clay, silt, sand, and organic solids. But that, I keep that fixed solids in there for, I'm not exactly sure, maybe for sentimental reasons, but in any event, fixed solids are a variable. We have 3 algal groups. Again, we'll talk about this more when we talk about the water quality model, but freshwater, spring diatoms, and other. And other is basically everything that isn't either freshwater or a spring diatom. Strictly speaking, you could make those three groups anything you want. The code just says you have three groups of algae which have potentially different characteristics. Looking at Chesapeake Bay, there's a spring diatom bloom in which the phytoplankton have very different characteristics. They're cold water creatures and they like salt water. They have very different characteristics than other algae, so we assign them their own parameters. In many systems or subsystems, the freshwater algae have very different characteristics than the saltwater algae. So we allow a freshwater algal group, so you can specify that the growth rate in the freshwater Potomac or something would be different than in the lower Potomac. So in any event, we have carbon groups, dissolved carbon, and three particulate carbon groups with different decay rates. And as we learn about the sediment diagenesis model this afternoon, we'll see why we allow all three of those. Ammonium, nitrate, algal nutrients, organic nitrogen dissolved, and then the three solids with different decay rates. Phosphate, that's dissolved inorganic phosphorus, goes by a lot of names. Keeping with the models for carbon and nitrogen, dissolved organic, and three particulate organics. A variable called particulate inorganic phosphorus, which we'll go into tomorrow. It's particulate, but it's not organic, and there's a lot of it in Chesapeake Bay. Chemical oxygen demand, that's things like sulfides, reduced substances, could be reduced iron, and dissolved oxygen. So those are what are active in the bay at this minute. Okay.
Because
Yeah.
in the previous slide, you have three particulate organic matters, but here you have two dissolved and two particulate.
Let's see. I have a feeling Richard and I need to get together on this.
Maybe, because
No, you've got the three. The thing is that the last three are way down here at the bottom.
Oh, okay. Okay.
Okay, and this illustrates a principle I was making before that,
G3, okay.
yeah, the G3s were added fairly recently. Let's go back up to here for a minute. The 30, 31, 32 are G3 carbon, nitrogen, phosphorus. Those are very slowly reactive, almost inert organic matter. We added those very recently. And, you know, these other slots, you know, the slot that I might have wanted to make it variable number 12, but 12 was already, or I might have wanted to make it 13, but 13 was already occupied. So I just slipped those in somewhere where they fit, given that I had 36. And I don't know if they might have been something else at some previous time, or they might have just been empty. In fact, it's interesting, let me go back. If you look at this, okay, well, in some of these slides, the number of constituent parameters was 27, which shows you it's an old slide or something. But in any event, so I added those three down at the bottom where they fit. So the order of the numbers of it, if you want to plot, you know, G3 phosphorus, you're going to specify 32. The table that I'm showing you just makes more sense, you know what I mean, to put it in that place. Okay, other questions, comments?
Will you talk later about how temperature and salinity are computed in ICM?
Excuse me?
Later, will you talk about temperature and salinity?
Yeah, it's not, salinity isn't computed at all, really. It's inert. I mean, yeah, but I'll talk, indeed, probably Thursday morning, we're going to get into temperature. Okay. NXCBC, NXHDR, NXS1, etc. NXCBC, this is really important, guys, so get this down, but, you know. That's next constituent boundary condition, next hydrodynamic model read, next S1 file, etc. I suspect this is a relic of the W2. It's the devil. The code, what it does is you have time variable inputs. Maybe we'll look at this in a couple of moments. All right, so let me explain first, then we'll take a look. You have time variable inputs. For example, the watershed model, you have an input every day. Hydrodynamic model, you have an input every hour. Point source loads, you have an input every month. So you can, the intervals at which you read information is variable. And it's not only variable, but I mentioned to you like 3 different kinds of information that come in at different times, but it could even vary within a file. So I'll give you an example. Suppose you had combined sewer overflow file. You get flows when it rains, but it doesn't rain every day. So you only would have inputs on certain days. All right, so what the model does is it reads this file, and what it does is it reads one step ahead so it knows when to come and read the next one. Imagine for a minute, we talk about a combined sewer overflow. Imagine we had an overflow on day 1 and on day 30. So I want to read those inputs on day 1 and day 30. So the model reads the day 1. How does it know when to come back and read day 30? What it does is it reads the next one, and it assigns that value NX. So it would be like S1 is a load file. So the value NXS1 would be assigned the value 30. When you're on day 1, it's going to read the next input and say, I need to come back and get this on that specific day. Go ahead, Jim.
Wouldn't you actually, if you wanted, you got a rainfall event in day 1 and day 30, wouldn't you need to specify a 2 to turn off the load?
You do.
Right?
We'll get to that.
1, 2, and then 30.
Yeah, we'll get to that nuance.
Okay.
But in any event, okay, so it's always reading ahead. Okay.
So it's not reading, the program is not reading the entire array in?
It does not. It does not.
Read in just based on that.
Yeah. That'd be a lot of store. If you think about 11,000 cells and 360 days, and that'd be a lot of storage.
But it would be faster, right?
Well, I don't know. I don't know. It could be.
Years ago, it was impossible.
Today it would be challenging, especially if you're doing 10 years, another multiple.
Right.
The reason this, I'm emphasizing this and mentioning this is you can get into a problem. Suppose you